Paul EMMETT, he was a very good friend with Linus Pauling. I think you heard that in several sessions yesterday. Both graduated from Oregon University in 1922. 1971, that was the first year when the same award was given for the very first time. Could I have next slide? And it was provided at the second NAM that took place in Houston. In 1971, the award winner was Richard J. Kokas. Could I have the next slide? Professor EMMETT has focused on a lot of different areas, but one area in particular that I would like to mention is the area of fuel synthesis and Fischer-Tropsch process. And while he was lecturing, Bert Davis, who is our honorary chair, has actually been able to videotape Professor EMMETT. And during that lecture, Professor EMMETT was focused on the energy crisis, early energy crisis in the early 70s. And he was talking about the importance of conversion of coal. And we would like to show a 24-second video right now. It was provided by Bert Davis. And after the video, we will introduce then, with the help of Alexis Bell, the award winner. Could I have the video?
The discussion of coal and energy situations usually starts out with a prolonged presentation of the facts as to the coal difficulty. Recently I heard Ed Teller, as a matter of fact, of interest to you perhaps. He's lecturing now on coal. And he treats coal as, he treats the energy crisis as a disease. And he goes through the diagnosis of the disease, the symptoms of the disease, and finally the cure of the disease. It's a very effective presentation. But I assume that everybody here is quite familiar.
My co-chair, Alexis Bell, to introduce the winner.
Thank you, Ushi. Well, it's a great honor and a pleasure to introduce Chris Jones to you, the winner of the 2013 EMMETT Award. Chris is a native of Michigan, Troy, and began his research on materials synthesis and catalysis while he was at Caltech, where he worked with Mark Davis. And he did both a master's and a PhD degree there in chemical engineering. And during this period, he received the Dow, or earlier Union Carbide Award in 1999 for innovation recognition of his work. Upon completion of his work at Caltech, he stayed at the same university, but he moved from chemical engineering to chemistry for his postdoctoral work, which he did with John Burkaw and again with Mark Davis, now focusing on metallocene complexes and their use in polymerization of olefins. After completing his postdoctoral work at Caltech, he moved to where he is today, at Georgia Tech, became a professor of chemical engineering there, and today he is the New Vision Professor of Chemical and Biomolecular Engineering at Georgia Tech. He leads a large group there that's devoted to the broad areas of materials, catalysis, and adsorption. I'm sure we'll hear parts of this work during his presentation. And he's been honored by a number of awards that he's received during the period that he's been there, the past 13 years, including the NSF Career Award, a DuPont Young Professor Award, and of course today the EMMETT Award. Also included in this year is the Curtis W. McGraw Research Award of the ASEE. He's also received the Apachev Prize from the ACS, and today he will receive the EMMETT Award, or present the lecture. So it's a great pleasure to introduce Chris, and before I complete my comments here, I want to say that I've known Chris virtually all of his academic career, and I've marveled at the success in which he's brought a knowledge of chemistry, and particularly homogeneous catalysis, to bear on the development of heterogeneous catalysis. And today, very appropriately, we will hear his lecture on learning about and learning from catalytic mechanisms with supported molecular catalysts. So Chris, come up to the podium, and we should all applaud Chris as he comes up.
All right, thanks, Alex, for that nice introduction. I really appreciate it. I'm honored to have the opportunity to share with you some research from my group over the course of the last 13 years at Georgia Tech with the title that Alex just mentioned. I'd like to begin by giving a special thanks to Grace Davison, the operating segment of W.R. Grace & Co., who has sponsored this award for a number of years and really has a very long and continued support of the North American Catalysis Society. Furthermore, as a member of the daughter organization of NACS, the Organic Reactions Catalysis Society, Grace has supported that organization for an extremely long time as well, and so I'm very grateful for that. I'm also very proud to be the 22nd EMMETT lecturer. I know a large fraction of the previous EMMETT lecturers and have enjoyed interacting with them and have been inspired by their research accomplishments in catalysis. So I look very much forward to working with these folks for the next several decades, and I hope to continue to interact with all of you in this community for many years to come. So if I had to describe my research interest in a nutshell, I would say that I'm interested in applications of synthetic chemistry to solve chemical engineering problems. And right now my group is working in three primary areas: molecular catalysis, heterogeneous catalysis, as well as adsorptive CO2 separations. Of course, today we're going to hear about those top two areas, and you'll notice in this slide that those two areas are separated by a dotted line. And this represents a long-term goal of mine in research, is to try to bring these two currently somewhat separate catalysis communities together. So if we polled everyone in this room today, I think we would find that the vast majority of us would consider ourselves practitioners of heterogeneous catalysis. And there's other meetings that are approximately the same size that occur nationally and globally each year that focus on molecular or homogeneous catalysis. But I think there's a lot that we can learn from each other amongst the different subdisciplines. And I think that going forward in the long term, to the extent possible, I'm hoping that everyone in each catalysis community, heterogeneous, homogeneous, and biocatalysis, can be inspired by the others. And at some point, we will all just simply consider ourselves catalysis scientists. I'd like to acknowledge all of the outstanding people that I've had an opportunity to work with. This is a list of, on the left side, the postdoctoral fellows who I've had an opportunity to work with at Georgia Tech, as well as the PhD students who earned their PhD while working with me. In particular, I'd like to highlight the folks in blue, including Quinn Yu, Xiaolai Zhang, Krishnan Venkatasubbiah, Nick Brunelli, John Richardson, and Chris Gill, as these are the people whose work I will talk about today. I'd also like to acknowledge the people who earn MSs working with me, as well as a number of international visitors that I've had spend time in my lab. All of the visitors always really enrich the interactions within the group. My current group is shown on the bottom and listed on the right. I have 11 outstanding PhD students, 6 postdocs, and 2 visitors, several of whom are here, and I appreciate their efforts. Okay. So I'd like to move into the first section of the discussion today, which focuses up on learning about mechanisms with supported molecular catalysts. And this work stems out of a DOE program, a DOE-sponsored catalysis science program that we began in 2003, whereby we put together a team of researchers to work on a particular focus area of developing model and hopefully stable supported molecular catalysts that we could use as model systems that would give us some general guidelines that we could use to design supported molecular catalysts. We focused in 2 areas. The first, palladium-catalyzed HEC reactions. The second, cobalt-salin catalyzed epoxide ring opening reactions. So the first is a building block chemistry whereby we can build complex organic molecules. The second is a chemistry where we can impart some chirality into structures. So we'll begin with the HEC reaction mechanism to give everybody a little bit of background. So the Heck reaction mechanism, if you look it up in a standard organometallic or inorganic chemistry book, will be shown on the left. Here you see that the pre-catalyst typically will be a palladium-2 species, usually a molecular species, that in situ under reaction conditions is reduced to palladium-0. This palladium-0 species can then begin to react with the reagents. In this case, we're going to be coupling an aryl halide along with an olefin to ultimately give a coupled product and then ultimately regenerate the palladium-0 species. So this palladium-0, palladium-2 mechanism is generally accepted. There continues to be some debate, however, on whether the catalysis requires a palladium-0 molecular species in solution or whether, in fact, it could occur on the surface of palladium-0 nanoparticles. Interestingly, in the early 2000s, late 90s, there was an alternate mechanism that also is a 2-electron mechanism oscillating between palladium-2 and palladium-4 that was proposed for some homogeneous systems. However, there was not a lot of definitive experimental evidence for those systems. So the palladium pincer complexes shown here were the complexes that we identified and chose to use as our supported catalysts in our Heck reaction studies. So these pincer complexes have tridentate ligands, as shown here, and the ligation could be PCP, as shown in the top left, SCS, as shown in the top middle, or NCN, as shown in the bottom center. And these are just several examples of palladium pincer complexes that had been made prior to our start, these coming in the late 90s, as shown in the reference on the top. And the reason we chose these complexes is they were known to be extremely stable in air and solvents at elevated temperature, and this is associated with the robust palladium-carbon bond that stabilizes that palladium-2 oxidation state. They're furthermore synthetically accessible, meaning we could functionalize the ligands easily and use synthetic chemistry to support them on solids, and low palladium loadings were needed. So typically in homogeneous chemistry, people would use perhaps 1 mole% palladium in the reaction, and then after the reaction, they would be able to recover and, in fact, recrystallize the complex. And this is what led them to hypothesize that this complex is extremely stable. And given that it's very stable in the palladium-2 oxidation state, this led in part to the hypothesis that perhaps a palladium-2, palladium-4 mechanism operated. This mechanism was first proposed in 1995, and from 1995 going forward was quite often cited as a possible reaction pathway for these pincer complexes. So we began working on this with a new approach that DOE was using at the time in 2003 to address catalysis science, and that was in the form of small teams. And I've really enjoyed working in small teams. I find them to be very effective. And this particular small team was built of myself, Marcus Weck at NYU, who's a polymer chemist. He was at Georgia Tech at the time and then moved to NYU. Dave Sherrill is a electronic structure chemist, physical chemist, who is looking at the electronic structure of metals and supported metal complexes. Pete Ludovic is a support modeler, so he would help us to model mesoporous oxide supports as well as polymer supports. And then, of course, everyone in this community is familiar with Bob Davis, who's a former EMMETT lecturer and was also part of the team focusing on in situ spectroscopy and kinetics. So our original goal was to take these palladium pincer complexes and try to develop an understanding of how they behaved as a function of how they were supported on the surface. So we began by making 4 palladium SCS pincer complexes as shown on the left. On the top is a soluble system, so this would be a typical homogeneous catalyst, and on the bottom was another soluble system that was, however, still supported. So this was supported on a polynorbornene polymer that we would have soluble under reaction conditions, but that could be precipitated. In order to do classical heterogeneous catalysis, we also had insoluble supports that we could pack into a column or recover via filtration. One was on a Merrifield resin that's cross-linked. The other was on a mesoporous silica SBA15, as shown on the right of the slide. This particular SBA15 was a typical one with pores about 50 angstroms in size, surface area over 800 meters squared per gram. Our Heck reaction that we chose to study was the coupling of iodobenzene with N-butyl acrylate. As shown on the bottom, this is done in DMF and triethylamine as base at high temperatures. So this is a pretty standard test reaction for these types of palladium pincer complexes. So I will show you a plot of conversion versus time, and our reaction conditions are shown on the left. So this is going to be our conversion time plot, but I start with only 2 data points at long times. And I show you the first run in blue and the second run in red. And if we simply were to look at the yields of the final product in long times, we might say that this catalyst looks quite stable and recoverable. We could use it once, get a high conversion and high yield, recover it, and use it again. And in fact, this is the way the literature in this particular subfield of catalysis looks, because the primary practitioners of HEC reactions are organic chemists whose main interest is not necessarily the fundamentals of the catalysis science, but how can I use catalysis as a tool to make a complex organic molecule that I'm interested in. So for that reason, what yield you get at a long time is most important. However, with our interest in catalysis science, rather than measuring yields at long times, we took full kinetic profiles. And literally in one of the first experiments in our project, we determined that we probably don't in fact have a catalyst that we've made. So by looking at these kinetic profiles, we can immediately see the sigmoidal kinetic plot that suggests that our catalyst is in fact a pre-catalyst. And unfortunately, or fortunately for us at the time, that shifted our focus in the project immediately away from making a well-defined stable catalyst to trying to understand what was happening under reaction conditions with our complex. So this brings me to a really beautiful review that was published in 2000 by Beletskaya. And the title of it is The HEC Reaction as a Sharpening Stone of Palladium Catalysis. And there's a few lines that I find extremely suitable at describing the state of the art in the early 2000s with this reaction, and I'm going to paraphrase them for you, and they're on the slide for you here. She states, "The task to comprehensively review HEC chemistry is now a hopeless adventure and would require a multi-volume set, as it has become one of the basic tools of organic synthesis. Indeed, however, whereas most reactions, particularly catalytic ones, are well-defined and specific to require some particular reagents and catalysts and to operate within a confined domain, quite often several general procedures can cover almost all conceivable applications, and yields for similar substrates can be extrapolated. However, nothing like this is true for HEC chemistry," she says. "The catalyst is often anything containing palladium, often in homeopathic doses or trace doses. All different solvent types have been tried, and none have been completely neglected. On the other hand, often a small variation of substrate structure, nature of the base, ligands, temperature leads to unpredictable results. An obvious question of what is the best catalyst and procedure remains unanswered, even for the simplest cases, though studied in hundreds of works." And so this is a really nice description of what the state of the art was with the understanding of the HEC reaction in the early 2000s, and it really inspired me and my group to try to focus in on understanding what was going on with our palladium pincer complexes. So if we look in the literature in detail, we see that there are a lot of supported HEC catalysts that are claimed to be recyclable and recoverable. But as I showed you with my first data slide, those claims are quite often based on the capability to reuse the catalyst where the reaction yields are reported instead of kinetics. And if we look in detail and carefully in the literature, we often will see that supported catalysts, for example, palladium on carbon that's used in these reactions, may act as a palladium reservoir, releasing trace active palladium species into solution during each cycle. So there are a number of papers in the early 2000s from both Asia and Europe that saw that for catalysts like palladium on carbon. So this plot here on the bottom right is a plot of the conversion, which is the black squares, along with the percent of palladium from a supported palladium nanoparticle catalyst that is leached into solution as a function of time. And you see that there's an induction period in the conversion, then there's a rapid reaction, and that reaction corresponds with leaching 35% of the palladium from the solid support into solution. And then after reaction, you see actually the palladium redeposits on the surface. So if we do the chemistry whereby we only take a data point out here at long times and then analyze the solution for palladium, we would never know that palladium went into solution. And so this beautiful work here with the palladium carbon system really shows that for that system, catalysis occurs in solution. Furthermore, there are other studies that show you exactly how much palladium is needed for some of these reactions. And in mid-2000s, there was a publication that got a lot of hype that was a transition metal-free HEC reaction. And then the same authors followed up a few years later, showing that in fact there was a 50 part per billion palladium impurity in their sodium carbonate that caused the catalysis. So for these HEC reactions, these coupling reactions, trace amounts of palladium can do all of the chemistry, and it can make elucidation of the nature of the active species quite challenging. So the questions we address then is are the palladium SCS and PCP complexes truly catalytic? And are they stable organometallics that operate via a palladium-2, palladium-4 catalytic cycle? So all of us in this community, if we were going to study leaching, one of the first things that we would all think to do is a hot filtration test. So in this plot of conversion versus time, our normal kinetic profile is shown in blue, and we could choose to run the reaction to 20% conversion and then filter the reaction while hot. In this particular chemistry, because it's air-sensitive chemistry, you need to do that while it's kept at reaction temperature, and also such that it doesn't get exposed to air. But if you do that, we would see that the reaction profile would continue as shown in red. So this confirms in our case that we had the presence of soluble palladium in solution that was doing the catalysis. We could further back that up with a second test, not wanting to rely on any single test. And a beautiful one that's been in the literature for a few decades is the three-phase test, as originally published in the mid-70s in JACS, as shown on the bottom. And in this reaction, we would tether the catalyst, in this case the SCS complex, to silica on one solid, and then take one of the reagents, in this case the aryl halide, and tether it to a second solid. So ideally, in the absence of any leaching, these two species would never see each other, with all of the remaining reagents and solvents being in homogeneous solution. And then we can monitor for reaction by looking for conversion of, in this case, the N-butyl acrylate in solution, and then we can recover the solids after reaction and analyze the solids via spectroscopy in order to see the coupled product that should be linked on this onto the second solid surface if, in fact, we got palladium leaching. And we could verify both of those with Raman and IR spectroscopy as well as conversion of the N-butyl acrylate, showing that, again, we have leached palladium that is doing catalysis. So at this point, we knew we had catalysis in solution, but we could not rule out catalysis occurring on the surface. So there's still the possibility that we had an intact pincer on the surface that was doing catalysis via this palladium-2, palladium-4 cycle. And in order to assess this, we chose to use a selective poison. And so we ideally wanted to choose a selective poison that would either poison only the mesoporous silica-supported catalyst or only the soluble leached palladium species. And we thought that we had plenty of polyvinyl pyridine in the lab for another project. This is a cross-linked resin. So just out of convenience, we pulled that off the shelf and decided to use that as our poison. The idea being that the resin beads are far larger than the mesopores of the silica, and the cross-linked resin's insoluble. So it should serve to extract free palladium from solution, over-coordinate it, chelate it, shut down catalysis, but it should not interact with any catalysis that occurs from sites within the mesopores. And if we do that, again with the conversion time plot shown here, and add the polyvinyl pyridine at the midpoint of the reaction, and this is the first time we did it here, so this is the historical plot, we again saw that the reaction was essentially extinguished. Polyvinyl pyridine is not the greatest poison for this. It happened to be convenient in what we had in the lab. We've used several other poisons since that time, and in fact a lot of commercial palladium scavengers that are used to clean solutions after reaction in the pharma industry, in fact, work even better as poisons. So this suggests that there's in fact really not any catalysis from these pincer complexes that had been thought to be novel catalysts that operated by a unique mechanism for approximately a decade. In order to try to put the nail in the coffin, so to say, we sought to do one additional test and to try to understand the nature of the leaching. So the two most likely bond rupture points were with the silane on the surface, which could be hydrolytically cleaved, or with the SCS bonds in the ligand. And if this bond break in blue, we could in principle have leached palladium pincer complexes that could then do the palladium-2, palladium-4 cycle, whereas if these bonds broke, we should get naked palladium species that should behave like, for example, the supported palladium carbon type catalysts. So the classic way to address this, again with a test that's been in the literature for now almost 100 years, is with a mercury test. So if we add mercury to this reaction, the mercury 0 will poison metal 0 type species like palladium 0, but mercury 0 should not poison molecular homogeneous organometallic complexes. So we did the silica-supported catalyst and the homogeneous catalytic tests in my lab, and then Marcus Weck's group did the polymer-supported catalyst in his lab with 2 different sets of people to make sure we got consistent results. And in all cases, when we add mercury 0, we saw no catalysis whatsoever. So the catalysts were completely dead in the presence of mercury. So this clearly suggests that there's not a palladium-2-4 cycle operating, and in fact, it's a classic palladium 0 mechanism that these pincers go by. So are these trends general? So after we did this initial study on the SCS, we thought there are a lot of other pincer complexes that have subtly different electronics on the ring. So we did 3 different SCS pincer complexes with different groups paired to the palladium carbon bond to alter the electronics within the ring. We also did PCP complexes, and they all behave exactly the same way, giving profiles as shown on the left. So in a plot of conversion versus time, the typical reaction conditions would be shown in blue, and you could get very, very high rates and high selectivities to your desired product. If you were to add molecular pyridine will compete with the reagents for binding sites on the leached species and slow the reaction, but it won't extinguish the reaction. So it's just a competition for binding with the catalyst. However, if you take those same functional groups and put them on a resin, the polyvinyl pyridine resin will give no activity whatsoever. And that's because when you put this on a solid, it can now chelate the palladium, over-coordinate it, extract it from solution, and extinguish catalysis. Similarly, mercury, if you add that at time 0, you get no turnover whatsoever. So these palladium XCS pincers are in fact pre-catalysts in these Heck reactions. And although we chose them because they were ostensibly stable and wanted to understand how to design ideal supported molecular catalysts, we had to follow where the science took us. And in this case, the science took us down a pathway whereby we had to determine what types of catalysis was going on with these systems. So to summarize this first section, by immobilizing palladium pincer complexes on several supports, we answered several questions that could not be easily probed homogeneously. We showed that these were pre-catalysts and that we had no evidence for any heterogeneous catalysis. And the catalysis was consistent with the palladium-0, palladium-2 mechanistic cycle. I think one of the nicest things that came out of this study was that a lot of the palladium organometallic chemistry community was focusing on these high-valent cycles, and a lot of people were trying to develop Heck, Suzuki, and related reactions that go by these high-valent cycles. And in fact, most of those go by palladium-0, palladium-2 cycles. But by trying to steer them away from this reaction, this Heck reaction, now there's a huge, vibrant community in organometallic chemistry that's doing a lot of truly catalytic, truly high-valent palladium-2, palladium-4 chemistry that's really revolutionizing organic synthesis. A lot of interesting CH activations going on. So we began this work in 2003 and published it in a series of papers going through about 2007. After about 8 years, we were able to actually make a supported, stable palladium complex. We published that in 2010, and it was truly recyclable with identical kinetics. However, it followed a different cycle. It was an oxidative Heck reaction, and it had slightly different reagents, and it was 2 to 3 orders of magnitude slower than the traditional Heck reaction. So while it is stable, it's not particularly useful. One of the top things that came out of this from our group, from my perspective, was this review paper that was published in 2006, whereby we tried to analyze the entire literature with different palladium pre-catalysts for Heck and Suzuki reactions, and trying to help guide the community in how to assess whether the catalysis was homogeneous or heterogeneous. And although this paper is now 7 years old, it continues to be, I think, an important paper today, and it's a good resource for anybody who's interested in palladium coupling chemistry. Okay. So in the second section, I'd like to talk about using knowledge of mechanism to design improved supported molecular catalysts. And in this topic, I'm going to focus on the cobalt-3 salin catalyzed bimetallic or cooperative hydrolytic kinetic resolution reaction, and I'll tell you about that reaction on the next slide. So this is a reaction that uses the cobalt-salin complex as shown on the left. So the salin ligand is a tetradentate ligand that binds your cobalt metal in this case. And because cobalt is cobalt-3 in this case, we have a counterion that's acetate. And Jacobson developed this catalyst in this reaction and published it in Science in 1997 and used it in this prototypical reaction, whereby we would take a racemic mixture of epichlorohydrin and use a chiral catalyst to select one of the 2 enantiomers to ring open with water to form the diol. That should, in an ideal case, leave behind an enantiopure epoxide that you could use in synthetic organic chemistry and give you an enantiopure diol as well. And one of the most interesting things that he discovered in his original work is that the reaction is second order in cobalt-salin complex. So this suggests that the transition state of the rate determining step contains 2 cobalt-salins in it. And in a beautiful follow-up work by, again, another former EMMETT lecturer, Donna Blackman, with Eric Jacobson, 7 years later they elucidated the molecular basis for this second order observation. And I'll take you through it here just so you have an understanding of this catalytic cycle. So you would start with a cobalt-3 complex, with X being your counterion. The sphere here around cobalt represents the ligand. And under reaction conditions, there's an initialization cycle whereby the X is added to some of the epoxide to open it, and in the presence of water that generates a second species, a cobalt OH species. And now you have two different cobalt centers in reaction, one of which acts as a Lewis acid and activates the epoxide, the second of which delivers the nucleophile in the rate determining step that involves two cobalt salins, ultimately liberating the two catalysts and the diol product. So this is a really nice example of a homogeneous kinetics paper, again by a former EMMETT lecturer. So if we're less familiar with kinetic resolutions, I'd like to just take you through what we expect to see. In an ideal kinetic resolution, we should start with a racemic mixture, so equal amounts of R and S. And after reaction, if the catalyst is perfectly selective, we would like to convert only one of the two enantiomers so that our total conversion is 50% and our EE of the remaining epoxide is 100%. And that might be represented by the conversion in EE plots shown in the solid lines in blue and red. So 50% conversion when you get to 99+% EE. A real, however, selective catalyst never only converts one enantiomer. You also convert at a slower rate the other enantiomer. So you might get to 99+% EE while converting 5% of the undesired enantiomer, giving you a 90% yield of your desired epoxide product. In that case, you'd get to 55% conversion when you got to 99% EE, as suggested by the dotted lines. So the kinetic plots I'll typically show you are plots really of EE versus time, because it's just easier to do that than to show you the EE and conversion plots simultaneously. So if we look at a plot of EE versus time, we're now operating at half mole% catalyst with the epichlorohydrin conversion with water. And we see for the homogeneous catalyst, we get a plot shown in black, meaning that in 2 hours we can get the mixture entirely resolved. And that gives us about 1 turnover per minute. That's a typical rate at half mole% catalyst for the homogeneous system. And in fact, if you support the catalyst in an improper way, if you take the catalyst and you isolate it on the surface, it can't interact with its nearest neighbors in that bimolecular transition state, and so the rate slows, as shown in blue. And if you look at how people previously had tried to enhance the reactivity by making supported catalyst, high local concentration of sites such that they can interact with each other, existing catalysts as of 2005 when we started, all were based on symmetric salins shown in red on the left. So you could have a symmetric salin that you could make into a linear polymer, as shown on the right with the red segments being salins, or you could have symmetric red salins acting as crosslinks if you made a polystyrene polymer using this difunctionalized monomer. So these symmetric salins are easy to synthesize because they have the same groups on each side. However, this is not a good design from the perspective of trying to promote that bimolecular transition state because it restricts mobility. So you would hypothesize that the more mobility your supported site has, the more likely you are to adopt the desired transition state. So we came up with this design for our catalysts. We wanted to have essentially a single functional group attached to the standard catalytic site on only one side. So we would fix the catalytic site, keep it constant in our studies, and again, keeping in mind the goal of the original DOE project, trying to understand how to best support molecular complexes for a variety of reactions, we wanted to systematically explore how the linker and the nature of the support impacted the ability of these cobalt salin sites to interact with each other. So our first thing that we did is we made a non-symmetric monomer. We could do this in one pot with high yield via a new synthesis that gave us essentially 88% yield of product that was non-symmetric, that we could then use as a platform molecule with which we could build a whole variety of catalysts. As an example, by having a non-symmetrically functionalized monomer, we could make a linear polystyrene whereby these cobalt salins would act as essentially side chains on the polymer, and that they would be positioned such that they could interact with each other in much the way as suggested by the Jacobson-Blackman transition state. So this design sets up these groups such that they can axially interact with each other. So we began by focusing first on the linker and understanding the role of the linker, in particular looking at the length and hydrophilicity. So now we're down at 0.01 mole% catalyst loading. So with the homogeneous catalyst, we were at half mole% catalyst loading because we had to have some statistical probability of these seeing each other in solution. But now that we've tethered them to a single surface, we can use a much lower catalyst loading. We're 50 times lower catalyst loading, so complete resolution under these conditions would be essentially 5,000 turnovers. So at this catalyst loading, if we have a rigid linker that's based on a phenylene, we get a rate that's about 5 turnovers per minute, or about 5 times more than the homogeneous catalyst at a 50 times higher loading. If we then go and increase the length of the linker by adding in flexible ether groups, whether it be 1, 2, 3, or 4, we see that first we can double the rate with a single additional ether group, and then by adding in 2 ether groups, we've now increased the rate by a factor of 10. And in fact, this becomes our best linker. As we go to larger and larger linkers, we see no increase in rate. And so for synthetic ease, we focus going forward on using this linker, whereby now we have a rate that's essentially 40 times faster than the homogeneous catalyst. So having a linker in hand now, we next sought to see what kind of impact we could make by changing the nature of the support backbone. And so most of these are going to be polymeric backbones because we wanted to have flexibility. And so we sought to make a very flexible linear non-styrene polymer, but we had to do it in a way that we could keep this cobalt saline as part of the reacting monomer. And one of the nice techniques to do that is with ring opening metathesis polymerization. So this is an interesting catalyst in that we did a catalytic polymerization using the Grubbs catalyst shown on the right to make our HKR catalyst supported on a polycyclooctene. And the goal was to make this linear polymer that would be highly flexible in solution. It's got a low TG, could adopt a random conformation, and should allow for effective site-site cooperativity. However, that's not what we made. So this was an example of a serendipitous discovery that in fact turned out to be very beneficial. So under reaction conditions, this ruthenium alkylidine complex is very, very reactive with olefins. And so the way the polymerization proceeded is that we would interact first with one of the octene monomers, insert it, and create the octene-based achillidine, at which point that octene-based achillidine would propagate with the rest of the monomer in order to make the linear polymer that we desired. However, this Grubbs catalyst is so active, it continues to look for olefins in solution. And when all the monomer's gone, the only olefin that's left is the olefin that remains in the backbone of the ring-open polymer. And so it will continue, then start to attack the backbone and essentially chew up and spit out small macrocycles from the originally linear polymer chain. So we start with an octene with a single cobalt saline on it, and then we get a mixture of macrocycles of different size with a dimer, trimer, tetramer, and then larger macrocycles that essentially look like donuts with pendant cobalt salines hanging off of each repeat unit. And the easiest way to see that this is in fact how the polymerization occurs is by following the gel permeation chromatography traces. So I show you here the monomer and the polymer that are formed even after 5 seconds of polymerization. Then 20 seconds, 1 minute, 2 minutes, 5 minutes, and 30 minutes. So after 5 seconds, we've already have some high polymer, but then after 20 seconds, you can already begin to see the intermediate oligomers that are forming being chewed off of this high polymer. After 1 minute, you see approximately equal size monomer, oligomer, and polymer peaks. And then after 30 minutes, we see that it's almost exclusively oligomers that we formed, with very, very little high polymer left and very, very little monomer left. Okay, so we've made these macrocycles via this catalytic ring opening metathesis polymerization. So if we then again look at the catalysis in the same reaction, the conversion of epichlorohydrin to the chiral diol at again 0.01 mole% catalyst, we see that we can get a good resolution using the mixture of macrocycles. But if we use just the monomer under these dilute conditions, we see no catalysis whatsoever. And it's because the probability at 0.01 mole% catalyst loading of this monomer seeing another monomer in solution is extremely, extremely low. So we had made a new catalyst that we thought was quite special, had a very high rate, and we'd like to compare it to others. But comparing the reactivity was challenging because people use different catalyst loadings. It's a bimolecular reaction, so comparing apples to apples was quite challenging. And so what we did is we made what we thought were the 12 best catalysts in the literature in our lab, and then compared them under identical conditions. And so what you see here is a plot of the initial turnover frequency in inverse minutes, going from 0 to 80, as a function of the catalyst type. Starting with the homogeneous catalyst at 0.01 or at 0.1 mole% catalyst in our standard reaction at room temperature, we got about 3 turnovers per minute. And if we went to our mixture of the macrocycles that I just told you about, we see that now we have a rate enhancement of about 40. So we had about 80 turnovers per minute by taking the same complex and putting it on this mixture of macrocycles. The next best catalyst in the literature was by Jacobson, published in 2002, which also has macrocycle structure, but where the cobalt saline is in the main chain, and it doesn't have the same type of flexibility that our catalyst has. It's about 10% reduced. If you then look at what would a heterogeneous catalyst look like, and you see that the rates are, and when I say heterogeneous, I mean filterable or packable in a column, so non-soluble. And if we make soluble components of it, for example, by having a polymer brush that's grown off a silica support, we can still get pretty high rates, about 15 turnovers per minute, with our best supported one that could be recovered by filtration being the polystyrene resin, which gave us about 20 turnovers per minute. And if we compare that to our isolated sites, again, it's worse than the homogeneous catalyst, 1 turnover per minute. And so we can have a heterogeneous catalyst that we can filter and work with very easily, but the most active catalysts are in fact soluble under reaction conditions. And in a really interesting discovery that was made by my collaborator, Weck, but that I didn't directly contribute to, was that we can now take this mixture of macrocycles, which I showed you had a turnover frequency of about 80, which is the most active catalyst known for this reaction, and now using preparative gel permeation chromatography, we can separate them into dimers, trimers, tetramers, and then mixtures of high macrocycles. And the majority of this polydispersed mixture is in fact dimers and trimers, but the dimers are completely inactive that we discovered by separating them out. And in fact, it's these higher macrocycles in the pentamer to decamer range that are the most active, but they only make up 5% of the mixture. So if you calculate the rates based on the pentamer to decamer, we're now an order of magnitude faster than that 80 turnovers per minute I showed you on the previous slide. And finally, in this section, we're trying to move in a new direction whereby we're trying to further explore how we can exploit this cooperativity. Can we take it towards other reactions and non-chiral chemistries? So in this case, we're interested in using alternate nucleophiles like methanol. And here we would like to selectively ring open to attack at the 1 carbon to create a secondary alcohol. So this is a regioselective reaction now with non-chiral catalysts. We've used racemic saline as well as a porphyrin. And in this case, looking at conversion versus time, we see the porphyrin is more active than the saline, so we can expand to other types of related ligands, L2-X2 ligands, such that we get 99% of the desired terminal product. But again, the rates are a little bit slower than the HKR. Now we're looking at about 3 turnovers per minute. So this only has modest cooperativity, suggesting that while there may be some bimolecular contributions, it's not nearly as strong as in the HKR case. So finishing the second section, we used previously existing knowledge of a cooperative mechanism in order to guide us in designing more efficient supported molecular catalysts. And by creating a new monomer that was versatile and could be used on silica supports, polymer supports, macrocyclic supports, we're able to develop catalysts that are highly efficient, and we're at now 10 to 100 times the state of the art. And we're currently extending this cooperative catalysis to other related chemistries using a similar family of catalysts. And this work has started in about 2005 and is now starting to draw to a close. So in the last section, I'd like to talk about using molecular and material design to yield new mechanistic insight and improved supported molecular catalysts. And in this area, we're working with cooperative acid-base catalysis with organic and organic hybrid materials. And so we'd like to try to take some concepts from nature and put them into simpler systems. This is something that I think heterogeneous catalysis scientists have said for 3 or 4 decades now, and we're slowly inching towards being able to do that. We could take inspiration from an aldolase type biocatalyst that uses a carboxylic acid and an amine as a paired acid-base site with the help of a hydrogen bonding residue from a serine. And we may ask ourselves, what types of these functionalities can we incorporate in a designed mesoporous silica catalyst? A bifunctional catalyst that would have acid and base. We focused on understanding the role of acid strength and understanding the role of spatial separation in our most recent work, and I'll share that with you here. So the very first project I started at Georgia Tech involved creating isolated amines on a silica surface. And ever since that first set of students, we've developed a good knowledge of creating amines on surfaces with well-defined structure. We originally used these to build constrained geometry complexes for olefin polymerization catalysis. Since then, we've developed a whole suite of supported amine materials that we now use in CO2 capture from flue gas or from air. And both in CO2 capture as well as in catalysis, the cooperative interactions of of the amine and the oxide are very important. They influence CO2 binding as well as catalytic turnover. But perhaps in this community we know that acid-base cooperativity in the form of amines paired with Bronsted acids most in this suite of three reactions: the Canova-Nagel reaction, Henry reaction, and aldol condensation. So it's been known for a number of years that acid-base catalysis is faster than base only. And all of these reactions, you'll note, involve coupling of an aromatic aldehyde, in this case, with another coupling partner, whether it be an activated methylene compound, a nitromethane, or an ketone. So if we look in the literature in 2003, Kubota showed that you could combine primary amines with silica surface to affect the aldol reaction and drastically increase the rate. Following on that, at about the same time, Alex Katz's group published a series of papers that conclusively showed that, in fact, it was the acidic nature of the silanols that was important in the reaction. So he went on to show that you could remove the silanols in an aminopropyl functionalized solid and remove them with a group that was either polar or nonpolar and have low rates. But if you had the silanols present, you would have very, very high rates. So building on this knowledge, we sought to further explore this chemistry. And in thinking about cooperativity with these types of groups, we can refer to a review paper from Davis in 2008 showing the different types of cooperativity that we might want and how we could design a catalyst for them. So we could have individual activation where A activates one substrate, B activates another. You could have dual activation where A and B interact with a single substrate. For this type of activation, you would like to design a catalyst that has a weak A-B interaction. So if this is an acid-base catalyst, you want to make sure the acid and the base do not interact with each other too strongly. For self-activation, however, where A must interact with B in order to activate the substrate, you would want to design differently. You would want to design for strong A-B interaction. And these chemistries typically are such that we would want to design for the blue way, whereby we have weak A-B interaction. And finally, you could have transition state activation, whereby you have cooperativity in the transition state of the slow step. So if we look at the reaction for the aldol condensation, which I'm going to talk about in this last section, we can follow it probably most easily with a bifunctional small organic molecule, proline, as published by Barbas in 2001. And in this chemistry, you'd have the acid that would protonate the ketone, making it susceptible to nucleophilic attack by the amine. That would therefore produce an N-amine as an important intermediate in the aldol condensation after loss of water. Then, with a second activation of the aldehyde now with the acid, you could have the transition state activation whereby the N-amine would attack the aldehyde to yield a coupled product. So in the context of that last slide, we can think of this first activation as a dual activation. You have both the acid and the base interacting with a single substrate. Whereas in the bottom right, we have a transition state activation, whereby you have A and B interacting with the two coupling partners in the transition state. So one of the things that was done prior to our work that we found interesting and inspiring was a look at the role of the acid strength. I alluded to the fact that we thought that we would need weaker acids owing to the fact that of the type of activation that we had. And the Davis group in 2007 studied 3 different acids coupled with a primary amine in a standard aldol condensation. And this is data taken from their paper. And they showed that with a combination of a carboxylic acid and amine, they could get very, very high yields. Whereas the phosphoric acid amine combination was worse, and the sulfonic acid amine combination was the worst. And so concluding that the weaker acids were more effective in this cooperative reaction. We were interested in further exploring whether there was an optimum pK of the acid. Are we better off to add the carboxylic acid or simply use the silanols that are available on the surface of the silica? And so we designed a series of catalysts that all are going to have the same amine loading throughout the rest of my talk of about 0.35 millimoles of nitrogen per gram. So this is a pretty low amine loading for those of you who work with supported organic catalysts. And we did the standard aldol reaction at 10 mole% catalyst, as shown on the top, the nitrobenzaldehyde with acetone. And if we do the catalysis with a conversion time plot with both amine and silanols present, we would get high rates as previously observed by Katz. If we then remove the silanols as Alex did, you see that the rates are drastically depressed owing to the removal of that acid component. We can then bring in a protected carboxylic acid, and we bring it in such that we don't remove all the silanols, we only remove some. So if we have a similar loading of the acid as we have for the base, we see that we've removed some silanols and the rate goes down. Now, if we deprotect this carboxylic acid and the acid aids the catalysis, we should see an increase in rate approaching the black line. If we deprotect the acid and it hurts the catalysis, we should see a depression in activity. So we thermally deprotected, and we saw a drop in activity. And so what this shows is that the silanols, in fact, are a better partner, and we can just extend that pKa table that was shown previously by Davis and say that the further down we go, the weaker the acid we get, the better we're going to be in this catalysis. And the final thing that we did is we looked at the variation of the amine length. So knowing that we want the amines to interact with the silanols in order to impart the catalysis, we are interested in knowing what is the correct distance, what is the ideal distance, and can we engineer that? So what we did is Nick Brunelli made a homologous series of different length amines. So everybody in the literature always works with the C3 propyl because it's commercially available. So we made the rest of the organosilanes so that we could go ahead and use the homologous series. Again, they're all going to be compared at exactly the same amine loading, both on the catalyst surface as well as in the reactor, in order so that we can have apple-to-apple comparisons. So starting with the C3, I show you a similar kinetic plot of conversion versus time, 70% yield after 4 hours. And interestingly, if we go to the C1, we see that the rate drops drastically. And in fact, we see that we proceed to about 10% conversion, keeping in mind we have 10% catalyst loading, and then the rate slows to a crawl. So it looks like we're creating some species that's inhibiting the catalysis. And if we go back to the mechanism and consider the mechanism, we can understand what's happening. So in the ideal mechanism, we have cooperative acid-base activation of the ketone to create the N-amine, as I showed you, and then acid activation of the aldehyde in order to make the coupled product. And we hypothesize that when you have this short methyl linker, the distance between the amines and the OH is just too far in order to affect cooperative catalysis. And so what that does is what that means is you can't activate the acetone, the amine remains free, and the amine simply reacts with the aldehyde to create an imine. Well, you would do that stoichiometrically. That would look like 10% conversion because we have 10% catalyst loading. And in fact, we can recover the catalyst after reaction and see via vibrational spectroscopy the clear signature of the imine on the surface. So we siphon off reactant into a catalyst resting state that's off cycle and doesn't allow for catalysis to proceed. We can verify this hypothesis by just taking a simple aminopropyl type group, putting it in solution in the absence of any protic species, and we get an identical kinetic profile. You go to a quantitative stoichiometric conversion to form the imine with the homogeneous catalyst shown in red and the heterogeneous catalyst, the homogeneous catalyst shown in black and the heterogeneous catalyst shown in red. So this is interesting because now we have an isolated base in a sea of silanols that can't interact with the silanols. And so this is a way to make isolated bases without having to put in capping groups. A C2, so if we increase the linker length now, we see that the rate increases slightly. So the rate is intermediate between the C1 and C2, and the linker is long enough to affect catalytic turnover. Interestingly, once we get to the C3, the activity plateaus. So we can go to a C4 and C5 and essentially get identical kinetics within the error of the measurement. So there's no increased inhibition due to a longer linker, and there's no increase in rate. We can go all the way out to a C11 and get identical rates. We were next interested in trying to see if we could tune the radius of curvature. So this mesopore silica that we used had a pore size of about 6.5 angstroms. The alkyl silane chain length is about 0.5 nanometer. And we thought that if we went to a smaller pore size, we could enhance the cooperativity between the amines and the silanols. And so if we go to a smaller pore size now, 2.3 nanometers, we see a totally different trend with regard to rates. Going to longer lengths actually inhibits catalysis due to steric crowding within the pores, and we get the same rate, identical rate, at shorter linker lengths. What was really fascinating, and is the last thing I'm going to finish up with, is by going to the nitroaldol reaction and just changing the coupling partner, we saw entirely different catalytic behavior with regards to the cooperativity. So by going from the aldehyde to the nitromethane, now we saw a continuous increase in rate, with this plot now being in turnover frequency and inverse hours as a function of linker length, up to the C5. And at some point it peaks, we don't know where, and comes down. So you get a volcano-type plot. And interestingly, again, the same trend exists for the small pore material. Now you have an inverse trend going from the low rate with the C4 up to a higher rate with the C2, because the C2 can now interact with that highly curved surface. By changing the size of the pores to an intermediate size, we can further enhance the rate. And by engineering just the length of the linker and the pore size, we're able to show that we can change the rate of the reaction by over an order of magnitude in this chemistry. So why is the nitroaldol reaction different? This is my last hypothesis, and it's owing to a subtle difference in the nature of the cooperative interaction. We believe that the aldol reaction involves a dual activation in the first step, a transition state activation in the second step, and that those are sequential steps involving one acid site. In contrast, for the nitroaldol condensation, we believe in the second step you require an additional acid site in order to stabilize the reactive intermediate. So this is merely a hypothesis at this stage, but we can see that by tuning the pore size and the amine length, we can begin to interrogate some of these subtle differences in the cooperative reaction mechanism. So to summarize, prior to our work, it was known that acid-base cooperativity would accelerate the aldol and nitroaldol condensation. We discovered that silanols are better partners than cooperative partners than carboxylic acids, and that we could tune amine silanol cooperativity by controlling linker length. Furthermore, we're beginning to elucidate the subtle differences between the aldol and nitroaldol cooperative pathways. We began this work about 3 years ago when Nick Brunelli joined my group, and we're just now starting to get publications out on the topic. So the overall summary is that we went back and forth between catalyst design and mechanism. In the beginning with the palladium system, we learned something about mechanism by a supported catalyst. In the second section, we already knew about mechanism due to the work of Blackman and Jacobson, and we could use that to make better catalyst designs. In the last section, we try to bounce between mechanism to catalyst design, and then ultimately, if we can figure out what's different about the nitroaldol reaction, going catalyst to mechanism. I'd like to thank the Department of Energy, Office of Basic Energy Sciences for supporting all of the work I showed you today and continuing to support our collaborative team. It's quite enjoyable to work with a team of researchers. I'd like to thank the people who have are currently funding me, and particularly I'd like to thank the Dow Chemical Company, who I've worked with for the past 5 years and have a long and fruitful partnership with them. Thank the companies who've sponsored my research in the past. And my final slide is to thank my Catalysis collaborators and mentors. So on the left are my current or recent Catalysis collaborators, and I'd like to thank the people who really catalyzed me into getting into Catalysis. That started with Levi Thompson at Michigan, who was my first research advisor. Then I went to Caltech, worked with Mark. Some of you may not know, but Mark is also a champion sprinter. If you want to make him uncomfortable, you can ask him about that. John Burkaw was my postdoctoral advisor along with Mark. Avelino Korma, all of you in this community probably know him quite well, one of the most supportive individuals you'll ever meet. He's been supportive of me since I was a PhD student. I want to thank him for his support. And then Bob Davis is my longtime collaborator, another former EMMETT lecturer who I've worked with for a long time. I was very fortunate to start my career on the West Coast with one Davis, and now that I'm on the East Coast, I get to collaborate with another Davis. It's been fruitful to work with both of them. And a final thanks to Grace for supporting NACS for a long time. I think we all really appreciate that, and thank you for your attention.